Hello everyone. Yes, I'm Minko, and today I'm going to be talking about how we can create faster Angular applications. So here are a couple of words about me, like co-founder and CTO at Rime.com, where in Rime.com we are building a platform which, by using virtualization in the browser, we want to help you build more scalable and consistent workshops and corporate trainings. And I've been quite active in the open source community. I'm a former member of the Angular mobile team, co-author of the official Angular style guide, maintainer and developer of Collizer and Angular Seed. And I've been writing some books about Angular. So here is a promo code for 50% off of my latest book, Switching to Angular, the 3rd edition. So as you can see, I'm quite excited about Angular. Like, I live and breathe Angular, kind of. Today we're going to talk about runtime performance of Angular. Usually when we're discussing performance of single-page applications, we're either talking about network performance or runtime performance. The network performance is related to just reducing the number of requests that we're sending over the network, reducing the number of bytes which we're transferring over the wire. And there is a lot of research going on in this direction. We have the Webpack team, who is constantly shrinking their bundles. We have the Google Closure Compiler team, basically they have a similar purpose. And we have the Angular CLI team, and they're providing very well encapsulated build, which does a great job in most cases. So what is left for us is just to make sure that we are not including many redundant dependencies, like to make sure what our dependencies are and what impact they have over the bundle size of our app, and reducing the number of HTTP requests. However, regarding runtime performance, everything is in our own hands. So in this presentation, I want to share a few simple steps how we can improve our performance. And they're kind of inspired by business applications that I developed over the past couple of months using Angular. So I faced some performance difficulties, and in this presentation I try to build a very simplified model of the business application that I developed, introduce as many as possible of these performance issues, and try to work around them somehow. So here is the super simplified business app. We have these two lists of items. And these are actually two departments in our business organization. We have a sales and an R&D department. We have the names and some performance data, which is just a numeric value for each of these items. And we also have an input where we can enter just new employees. We're assigning some numeric value to them, and right after that, going through some heavy business computation, which can be anything, business specific. So this is our application, and in general it has only two components. This is the static component tree, where we have an app component, which wraps the entire application, and two instances of an employee list component. Since the employee list component is the most interesting for us at the moment, let's take a look at its template. As I mentioned, we have an input, and in this input we have just the banana in a box syntax for two-way data binding, where we are binding the input and the value of the input to the label property declared inside of the controller. We also have an ng4 where we're listing the individual employees. So this is something quite simple. And in the end, of course, we're printing some information about these items. The label of the item, which in this case is just the name of the employee, and we're calculating a numeric value for each individual employee, just using some mocked calculation. We're going to take a look at this in a second. Here is the implementation of the employee list component. You can notice that we are not holding any state right here. So in general, the app component is passing the state down the employee list component. In this case, we can think of the app component as some kind of a container component or an information expert. So the calculate method, as I mentioned, it is mocked. So I'm using Fibonacci here because we really don't have to couple this presentation with something specific, like standard deviation or whatever my specific calculations in my specific applications were actually. The good thing about Fibonacci is that it has pretty much the same characteristics as the business calculations that we may want to apply, and it can be implemented in a very inefficient way. So we can stress even further how big performance impact going through heavy computations may have in our templates. So we're slowing down our application kind of artificially here. As recap, we can say that our application has an app root component, which holds the state, and two list components, which list component just visualize some data. And for each individual entry, we're just performing a heavy computation. So that's it. Let's see how this behaves with some kind of real data. So in this case, we have in total of 140 entries. Not that many. Let's just try to add a new entry in the sales department. So just look at the user experience at this point. It's terrible, right? It's super sluggish. But what does make it that slow? If we take a look at Chrome DevTools, we can see that our calculation gets invoked far too often. And that's the case because on each key press, Angular is going to trigger change detection for the app component, because that's how change detection starts from the root components of our app. After that, it is going to go in the first order, invoke the change detection in the employee list component, go through all the child components, where it is going to calculate the numeric value for each individual employee again, and do the same for the right-hand side of the component tree. So in general, we are recomputing the numeric value for each individual employee, although we haven't changed anything. We haven't gotten a new list of employees, so there is no point recalculating everything. So do you have any ideas for optimization here, where we're going to recompute the numeric value for each employee only when we get a new list? On push, yeah. Yeah, we can use on push or even change detection ref. Both are pretty valid. So with on push, what we can do is just to set the change detection strategy of the employee list component to on push. And in this case, we're going to trigger the change detection for the employee list component when it gets a new value for its inputs. So this makes sense. This means that passing a new reference is going to trigger the change detection. But does this mean that we need to copy the entire list of employees every time when we add a new item, or let's say when we remove an item, when we apply just some mutation over the item? That's going to be actually quite inefficient because of several reasons. First of all, we're going to copy a huge amount of memory, right? So if we copy this means that it needs to be garbage collected like the previous version of the list. And second of all, we need to loop over the entire list, which doesn't make any sense. What we can do instead is use some kind of immutable data structures. And immutable JS, I'm sure most of you are familiar with it. It performs great implementation for immutable lists, what we're going to need in this case. And it is implemented in a smarter way by using persistent data structures internally. So immutable JS is going to help us with two things. We're going to get a new reference to a list when we change it. And we're not going to copy the entire list. We're just going to reuse as much as possible from the previous list, because the persistent data structures, they perform some kind of structural sharing inside. And well, the optimizations, actually the refactoring that we need to do in our app component, they're pretty simple. We can divide them in two separate categories. First, when we apply a mutation to the list, we're going to get a new reference, so we just need to return it. And right after that, assign it to the property which holds this data in the app component. After that, this new list is going to be passed down the component tree. Our employee list component is going to get it. And since it uses on push right now, since Angular is going to determine with the reference check whether the input has changed, it is going to run the change detection. So that's pretty much it. Let's see how much faster we got. Now, when I was working on my application, I was expecting some huge performance boost, right? And here is the typing experience. So not too much better. In order to make sure that I did at least something useful, I wrote a bunch of end-to-end tests and run them through bench press by Angular. And they return me some pretty useful benchmarks. So I realized that I've gotten about 3 times faster, but that's still pretty terrible user experience, because we have only 140 entries in these lists, and it doesn't make sense to slow down the typing that much. So if we add log statement in the calculate method of the employee list component, we can see that, well, the calculate method still gets invoked quite often. But notice how this time we're invoking it only for the sales department. So we're not invoking it for the R&D department. So we're triggering change detection only in some part, like some isolated part of the component tree. And this is due to one very important catch in the on-push change detection. It's going to invoke change detection in given component, not only when it gets a new reference to any of its inputs, but also when an event inside of this component happens. Well, we can fix this quite easily. We can just do some refactoring, and with this refactoring, we're not only going to improve the performance, but also enforce better separation of concerns, because that's one of the criteria for writing more usable code in the end, right? What we can do is move the logic for the user input into a name input component. So this is going to contain our input with the ng model binding there. And we're going to move the list component, like all the list items, into the list component. We're going to change the change detection strategy of the list components to onPush. And the employee list component is just going to use these two components in order to fulfill its purpose. Here is the typing experience now. It's actually what you would expect from a text box. It's so much faster, and this is so much faster only because we are triggering the change detection only inside of the app component, the employee list component, and the other instance of the employee list component. We have isolated the events which are happening only in the name input component, so they don't impact the list component in any way. And here are the benchmarks. In general, we got about like a couple of hundreds or thousands times faster, only just by doing these three simple steps. Changing the change detection strategy to onPush, doing some basic refactoring, and using immutable data. Now let's see what the performance of our application is going to be when we add an item. So keep in mind that when we add an item to our immutable list, we're going to get a new list. We're going to pass this list down the component tree to the name input component, which is going to pass to the list component, and we're going to recompute the numeric values for each individual item in the list, which kind of don't make sense because, well, we have calculated the numeric values for all the employees except the new one that we are adding, so we don't have to recompute everything. Well, in order to fix this, we need to take a look at our Fibonacci implementation. As I mentioned, it has very important characteristics which are common for most of the business calculations that we use on a daily basis. First, it performs no side effects. So we're not going to send any requests over the network in the Fibonacci implementation, and we're not going to lock anything into the console. And it is going to return the exact same result when applied to the same set of arguments. And functions like that, in the world of functional programming, are known as pure functions. Well, in Angular, we have a concept which is somehow inspired from pure functions, and these are the pipes. So we have pure pipes and impure pipes there. Pure pipes, they're just pure functions in the end, and impure pipes, they hold some state, for instance. For example, we have the async pipe, which is impure, and the date pipe, which is pure by default. Now, well, let's try these two expressions. The first expression just applies a date pipe to birthday, and the second one just applies an impure version of the date pipe to birthday again. The output of the Angular compiler is going to be this thing here. Not too readable, but we can notice that check, there is one more additional check which is added for the pure pipe. So this CK here is going to compare the previous input of the date pipe with the current one. If they do not differ, well, Angular is not going to recompute the expression. Otherwise, it is going to invoke the transform method of the date pipe. And in the other case, Angular is always going to invoke the transform method of the pipe. So basically, the difference between pure and impure pipes is that Angular is going to execute the pure pipe only when it gets new input for it. We can very easily refactor our application to use pure pipes. So we have the calculate pipe here, which delegates its execution to Fibonacci. And we have the list component, which now, instead of directly invoking calculate, just applies the calculate pipe. Now, if we bench press this, we're going to get another performance boost. So this is another end-to-end test written with Protractor, and here are the results. So it's still quite faster. Well, now let's apply our final optimization. Now let's see how fast the initial rendering is going to be if we have 1,000 items into the list. So in this case here, we imagine that we have optimized the network performance of our application dramatically. For instance, we have 50 kilobytes of bundle size, and we're sending only one request to the network. Well, our rendering is still super slow. As you can see, it takes about 9.5 seconds to render the application. So, well, we need to bet on computational performance as well. And in order to improve it, in order to reduce the calculations which are happening initially, we need to take a look at our data. So in our data, we can notice several things. First of all, we're invoking Fibonacci for a very common set of values. We have Fibonacci of 27, 28, and 29. In my specific case, in my business application, I was invoking my business-specific, domain-specific calculation for pretty much the same values all over again. So we have samples from very small range. And during the initial rendering, we're basically recomputing the same value all over again. An obvious solution is, of course, to apply caching. So once the value has been computed, we're just putting it into the cache. And the next time, instead of recomputing it, we're getting it from the cache and just returning it. And well, in functional programming, we have a word for that, like a terminology for that. That's memoization, which is possible for pure functions. So in this case here, we can apply memoization to our Fibonacci just by getting the memoize function from Lodash and invoking it with our implementation. So this is going to return a new function, which is going to apply memoization. So when we invoke the memoized version with some arguments, internally, it is going to go through the computation, cache the result, and the next time when we invoke the function with the same set of arguments, we're directly going to get the result instead. If you prefer a more object-oriented way of doing that, there is a decorator, which I recently released. That's the memo decorator, which you can just place on top of any of your methods. And now this method is already memoizable. Well, if we run our application again with the memoize decorator, we're going to see that it's still slow, because there are 1,000 items, but it's still much faster, about 3 seconds faster. Now, there might be the question, all right, so what's the difference between pure pipes and memoization? Aren't they kind of the same thing? Well, with pure pipes, when we apply given pipe to, let's say, 27, Angular is going to delegate the calculation to Fibonacci, and after that, get the result. The same is going to happen for each next entry, although we have the same argument. However, the difference between pure and impure pipes is going to be that the transform method is not going to be invoked. So Angular is not going to go through this kind of computations on the next tick of the change detection, unless the arguments have changed. With memoization, the things are going to happen this way. We're going to invoke calculate of 27, going to go through Fibonacci, calculate the result, put it into the cache, and right after that, on the next invocation, we're going to go to the cache, get the result from there, and directly return it. We're going to do the exact same thing for each next calculation. So this way, we're saving a lot of computational time. And well, the last thing that we're going to take a look at is how we can optimize our ngFor. So about 99.7% of software is in the end just visualization of lists, right? And there is this rumor in the internet that when we apply a custom track by function, ngFor is going to be faster. And that's not exactly the case. Well, ngFor is smart enough to figure out when given element from a list has changed in order to re-render it. And for this purpose, it uses track by, but only in order to determine the identity of the items. So let's just take a look at a specific example. In this case, we have the list A and the list B. And first, ngFor has rendered list A. The second list that we're passing to ngFor is list B. Now, ngFor needs to compare these two lists in order to determine what it should render on the screen in the end. So it is going to compare the items by using the track by function. It is going to find out that the ID in this case of the first item from the first list is the same as the ID of the first item from the second list. Find out the exact same thing for the second items, and unfortunately for the third items, it is going to find out that we have a change. Well, the default implementation of the track by functions is just the identity function in the end, so that's the difference between having a custom one and using the default one. For immutable data structures, very often the same identity has just two different references. So in this case, it's very useful to implement a custom track by function, but in general, the default one is pretty much perfect for us. And as a very quick recap, on push change detection strategy, we can shoot ourselves in the feet sometime with it, because it is not going to trigger the change detection only when our component gets new inputs, but also when an event inside of the component happens. Also, there is important difference between pure pipes which can be considered referentially transparent, and memoization, and well, track by is not going to solve our problems always. Here are some links. Basically, I have described everything here in much more depth in these links here. And thank you very much for your attention.